Cette conférence va maintenant être enregistrée.
Merci. Donc, je suis chercheur, je m'appelle Francesco DOvidio, je suis chercheur au CNRS au même laboratoire que Josiane. Aujourd'hui, on va parler du couplage entre physique et biologie dans l'océan global, dans un contexte de changement climatique. L'objectif, c'est de faire autour d'une heure et demie. Et j'ai pensé de séparer ma présentation en 2 ou 3 petites parties pour donner la possibilité de faire des discussions avec vous, comme on ne se voit pas directement. C'est plus compliqué de me rendre compte si tout le monde est en train de s'endormir, si j'ai l'impression que vous êtes bien intéressé ou pas. Donc avec les pauses, on échangera sur le contenu que j'ai présenté. On va commencer. La première partie, le message à première vue est assez banal. Donc ce que je vais faire, c'est de mettre l'accent sur le fait, si vous voulez, sur la diversité entre un paysage terrestre et un paysage dynamique dans l'océan. Je me concentre en particulier sur l'océan pélagique, c'est-à-dire la partie de l'océan que loin des côtes et loin de la bathymétrie, et donc qui est contrôlée essentiellement par la dynamique des courants. Josiane, est-ce que c'est bien de le faire en français ou je peux faire aussi en anglais ou sinon, is it fine for everybody if I speak in French or do you prefer English? To me, it's exactly the same. If anybody prefers English, please speak now. Okay.
I would prefer English.
Sorry?
I would prefer English.
Okay. So we will continue in English. So the main point of the first part is apparently trivial. I will put the emphasis on the differences that we have between a terrestrial landscape and an oceanic landscape, a seascape, as sometimes is referred to. And I will focus on the pelagic ocean, so on the ocean upper layer in the open ocean zone. This means that we will study some cases in which there is no a fixed topography or a fixed coastline which can provide a reference which is fixed in space. On the contrary, the open ocean is controlled by currents, so that biological interaction with the physical parameters and among organisms themselves is mediated by currents. And we will see some tools that can be used to capture this dynamical process. Once we will have done this, then we will go to the second part, in which I will make a zoom on the Southern Ocean, and there we will be able to see more in details the structure of the trophic chain and some issues that are in conservation. On the background, some things that will come along are the context of climate change and the use of marine protected areas as a tool in this context. So let's start from this point. This is from the IPCC report on the ocean and the cryosphere. We see here, I think you are familiar with this kind of figures. There are two scenarios that are plotted over this figure. RCP 2.6 and 8.5. 8.5 sometimes is referred as business as usual. So this is what we expect if the emissions are not cut. and 2.6 is a scenario in which there are critical changes that are done to reduce emissions. These are in the figure we will see the effect of climate change on net primary production. So basically on the biomass that is provided in the open ocean to the trophic chain by phytoplankton, and the response in terms of total animal biomass, and also in particular in some services that the pelagic ecosystems can provide to us, like for instance fisheries. In general, what we expect is that with warming we can have a more stratified situation in the open ocean, which will correspond to an increased difficulties for nutrients to reach the photic layer from the interior of the ocean, which is reflected in turn in a reduction of primary production, with a consequence on the ensemble of the trophic chain. You see that there are, like in the Southern Ocean, some region in violet, which correspond on the opposite to an increase of primary production, and this correspond also in the Arctic. This correspond to regions that are on the opposite, limited in light, so that an increase in stratification due to global warming can lead to more nutrient that is injected into the trophic chain. This is another figure from a recent review, which shows the sensitivity of key ecosystems to 3 of the main impacts of climate change to the pelagic, in general to marine ecosystems. I talked about warming, but warming is not the only one. There's also acidification and then sea level rise. Sea level rise in the open ocean is not such an issue, but of course it is critical for ecosystems close to the coast. So the main conclusion from these 2 slides is that if today you are a marine organism, you are in trouble because of climate change, but actually your problems are not over, because there is also another risk to die. It's because of fishing. And we see here 2 maps that describe the fishing pressure around the globe. On the top panel, we can see the fishing effort in terms of hours per kilometer square. And in the bottom one, the units are a bit different. The effort is given in energy spent for fishing, so in gigawatts of engine power. There are 2 information. One is in terms of space, and the other in terms of time. In the upper panel, we see that there are very few regions that are not under heavy fishing pressure. We can see the Southern Ocean that has a special regulation, and also some species which are not at the moment economically interesting, but it can become in the near future. And then we see that there are some holes in the middle latitudes in the rest of the oceanic regions, which correspond to marine protected areas. It is interesting to see also that in the Eastern Africa there's a region which has no fishing effort. This is a very special marine protected area that nobody has declared, but which exists because of pirates. Now, if we look at the bottom picture, here the main information that we can extract is that the effort is growing at an exponential speed, which corresponded in the 50s and 60s to a very strong increase in catches, with a situation that has changed in a dramatic way in the 70s and 80s, in which there is a very slow increase in catches until the 90s. And today, in order to keep a constant rate of catches, you see that the effort has to basically double every 10 years or so. So the society is very aware of this problem. We spoke now about the impact of climate change on marine ecosystems, but this link is not in only one direction. There are also feedbacks from marine ecosystems toward the climate. This has been in some sense indicated in this IPCC report about 1.5 degrees, which consider several pathways to a decarbonized economy. In this figure, I want to remark the yellow part of the plots, which is indicated with these backs, which correspond to bioenergy with carbon capture and storage. In this part, there is also the active role that marine ecosystems can have in our trajectories for the future in terms of sinks of carbon. This can be if we increase the storage capacities of the carbon content of some marine ecosystems. This is what is called the blue carbon. Or another aspect that is included in this yellow part of the plots is the bioengineering, geoengineering effect that you can have if you act over marine ecosystems. This is a very sensitive subject with a lot of dangers on it, and if we have time, we will briefly speak about it in the end. Anyway, because of either because we see marine ecosystems as an heritage to protect, or because we see it as a possible tool and a part of the biosphere in our way toward reduced carbon emissions, we have interest to protect marine ecosystems. And so there are many efforts today to create marine protected areas around the world. There's a trend actually today which is from coastal marine protected areas to large open ocean marine protected areas. I think, well, there's a reference where you can have more details about the role of marine protected areas, the link between marine protected areas and climate change. But in general, there are three categories of issues that can be cited. The first one is about resilience, the fact that a marine protected area can remove some pressure due to fishing and human presence over marine ecosystems, so that they can be more resilient toward climate change. Then the second issue is what I mentioned just before, to see ecosystems as a provider of biogeochemical services, like for instance what is referred sometimes with the word blue carbon, and the fact that a climate ecosystem can store large quantities of carbon and can even buffer acidifications, like in the case of kelp's forest in coastal ecosystems. And then the third issue is refugees. This actually is quite interesting. You can think that you may want to protect regions which are more affected by climate change because they are more fragile. But in fact, there can be another strategy, which is to identify regions that are less affected by climate change and preserve them so that you are sure that there are some species that can have their environmental niches preserved and that can be recolonized the rest of the ocean in a future, which we hope will not be too distant, in which we can revert to pre-industrial levels in terms of temperature and other oceanic physical parameters. So this was to indicate the importance of marine protected areas and the three main issues which relate to them to climate change. So what is the state today? This is a map that actually is a bit old today. I think it's from 2017, which shows in dark blue the extension of marine protected areas around the world. There was actually back in 1992 a target to which the nations established, the signature of the parties that signed the Convention on Biological Diversity, which aimed at preserve 10% of the ocean with marine protected areas. About 2-3 years ago, we were at 7%, and this number has not risen a lot today. So there's still some work to do, with the 10% having been reevaluated at 20% level from recent works. France, in this regard, is a bit at the frontier because it has declared an ambitious objective to reach 30% of their waters. We will see at the end how this is proceeding. So a lot of work to do, and you see the interest in going to the open ocean, in the sense that the coastal environments, even if they are under a direct human pressure, and they can host very diverse ecosystem, are anyway very small in terms of surface. The open ocean, for sure, hosts very large spaces that at the moment are affected mainly by direct human presence in terms of fisheries. In the future, there can be mining as well, and fishing to some other species that today have no commercial interest. And these issues explain why today there are some trends to define large marine protected areas offshore. So, from a scientific viewpoint, there are many issues when you work offshore for a marine protected area. For instance, the problem of a juridical framework to apply. But let's put this on a side at the moment, and let's look at the problem from an oceanographic viewpoint. In this case, when you are in the open ocean, the main difficulties that you face is basically how to draw a line. We are terrestrial organisms. So for us, it is easy to think to a terrestrial ecosystem like the one that is depicted in the figure on the left. There you can see that there's a mountain range. There's a contrast in primary production. You can imagine that there's a forest, and you can also imagine some physical factors that can affect this ecological contrast. Probably there can be difference in precipitation and temperature due to interaction between the mountain range and the local meteorology. When you look at the ocean, the idea of a line is much more difficult to imagine. We have the impression that everything moves and is mixed together, so that at the end we are facing an environment which is much more homogeneous than on land. This kind of thought has a strong impact in terms of decision making, because when you want to protect a region, you may be tempted in the open ocean to simply protect the region which is less interesting, for instance, for fishing, if everything is more or less homogeneous. But this actually is not at all the case. It's enough to look at the ocean, not with our eyes, but with satellite instruments, for instance, and then you can see that there are some contrasts in the ocean, like the contrasts that are depicted in this picture. I showed here a region around Kerguelen Island. So these are waters which are part of the waters in these figures are inside the French economic exclusive zones. We will see much more details about these patterns in the second part. Here, the meaning of this these figures is very qualitative, and I want just to remark the contrast. The dark blue corresponds to basically a desert, a region with a very weak primary production, compared to the dark red, which is the equivalent of a dense forest. It's a forest not of trees, obviously, but of microscopic organisms, still the base of the trophic chain up to large predators. If you look at the other three figures more on the right, these are pictures that are derived from analysis of surface currents measured by satellite. And then you can see the equivalent to the orography, to the presence of the mountains. These, however, are the currents, so are very dynamical features which change in time while animals moves inside them. The white rings that you see in the middle image correspond to vortices, mesoscale eddies, and then the energy, the kinetic energy associated to these features are on the picture on the extreme right, while in the bottom picture all the filaments in red and blue correspond to steering patterns which are induced by the presence of the eddies, which can provide intrusion of waters with contrasted characteristics for hundreds of kilometers, and eventually mixing of these waters together. So we have a very contrasted landscape with contrast which we have to take into account if we want to study biophysical processes in these regions, included biogeochemistry like the carbon cycle, and if we want to establish conservation policies. We have also some tools like satellite instruments that allow us to extract information about this contrast. Now, let's see in very general terms how we can plot the ranges of the features that I showed. This is a very sketchy a cartoon of the ocean circulation in terms of space and time. So if we look at the ocean from very far away, the scale of thousands of kilometers, then you see the large scale circulation with the boundary currents, the upwelling systems. And you can see their change from year to another, from a decade to another. If you zoom, so if you approach the Earth and you are able to resolve features of about hundreds of kilometers, then you see that this large-scale circulation is actually very similar to what for us is the atmospheric meteorology. So there are, it is full of cyclones and anticyclones, which in oceanography we call mesoscale eddies, which are very energetic. They can have lifetimes of the order of months and control the redistribution of water mass on the scales of 100 kilometers. And then you can go even more close to the surface, and then if you resolve the surface of the ocean at the resolution of the order of few kilometers, you see that these mesoscale eddies actually are made of filaments around them. This is the submesoscale nature of the ocean, with features with lifetimes of the order of days to weeks. So today I will focus on this part of the ocean dynamics. Well, we can be even at a smaller scale, up to millimeter and smaller. But today, anyway, I will focus on this part for two reasons. The first is that if you look at the time scale of the mesoscale and the submesoscale, these features have a temporal variability of the order of days, weeks, and months, which correspond to times of ecological relevance. If you look, for instance, at the development of a phytoplanktonic bloom, then there's in the middle latitude there's a big growth of phytoplankton with durations of the order of a few weeks. And then even if you look at the trips of megafauna species which explore the ocean to find to feed, then you can see that oh, sorry, I have to take the charger, so a small pause. Okay, I apologize. So even for megafauna species, their trips to feed are of the order of weeks and days, weeks, or months. In this regard, you can think to the submesoscale and the mesoscale, together the fine scales, as a part of the ocean physics that can structure strongly the marine ecosystems in the open ocean. There's another interest in terms of climate for studying the fine scales, And this is the fact that if you consider climate resolving models, so models that can have the possibility of resolving patterns on the entire planet, then the resolution is limited typically to features of 100 kilometers and more, so that the dynamics of the fine scale is not explicitly represented. Understanding in this regard the way in which biogeochemical processes develop at this scale is very important for parameterization purposes. So for being able to represent implicitly the processes that a climate resolving model cannot represent explicitly. Okay, so this is another example in the Eastern Mediterranean, in which you can see some eddies and some filaments, which are not visible at the naked eye. And then let me make just a small pause of a few minutes to ask you if you all. I try to stop sharing, and do not hesitate to switch on your camera so that we can see. To me, it feels very strange to speak alone in in my room in the silence with some letters on the screen. So you're welcome to switch on your camera and the microphone. Could you follow? Was it easy to follow? Did you understand the main message from this? Okay. So is the question about marine protected areas something that interests you? Do you, anybody would like to comment about this? In this course, I think you see very different aspect of climate change.
Just I have a question. So
Go
you
ahead,
said
please.
on one figure, like there were like 6.35% of the global ocean covered by protected area in 2017. So what's the situation now in 2020?
I don't know the number, the exact number. I think it is a bit larger, but not, but still not 10%. It's probably 7 something, I would say.
And you said like the project for France is to
It's
go
30%, yeah.
30%, but when?
Yes.
Like in 20, 30 years, the end of the century, or?
No, it has been announced. I think it was an objective of for the end of the presidency of Emmanuel Macron. So it is an objective at on a very short time scale.
Okay.
This also, please check it, but I think it's on a short time scale. Yeah. And France has the advantage of having a lot of economic exclusive zones in the open ocean, and some of them are in a regions which have a negligible human population, like in the Southern Ocean. So in some sense, for France, is a bit easier than other countries which can have a very long coastline around their country. And for this reason, for instance, France is doing a lot of work to establish marine protected areas in their territories in the Southern Ocean, including the scientific work that goes together to assure that the marine protected areas are not in regions which are just uninteresting from an ecological viewpoint. Are there other questions? Otherwise, I will continue. So very briefly, I want to show you some of the tools that can be used to analyze the open ocean marine landscape. The first tool is satellite altimetry. Satellite altimetry is one of the most important tool in observational oceanography, but because it allows to estimate the surface currents in the ocean. The principle is a radar instrument that can measure the distance between the satellite and the ocean surface, and the deviation of the sea surface height from a spherical or a geoid shape due to the presence of the current. The differences are not huge. Here you can see a map of the surface currents together with in color what the satellite can measure. So you see that the differences are of the order of few tenths of centimeters, associated with cyclonic and anticyclonic structures. A hand-waving explication of the relation between the currents and the sea surface height, you can think in this way. Because of the Coriolis force, when a water parcel moves, there's a force which acts on the right in the northern hemisphere and on the left in the southern hemisphere. So if you are, for instance, along this this line, do you see the arrow of the cursor when I move it?
Yes.
Okay. So you can imagine that the Coriolis force is acting this direction on the right, because we are in the northern hemisphere, and so there is some water that is accumulated on that side, not but there's a limit to this accumulation, that is the pressure gradient that acts in the opposite direction. So at the equilibrium, the speed of the currents can create a force that is balanced by the pressure gradient of the surface of the water that tries to go back to a flat case. By measuring the deviation of the sea surface height from the geoid surface, then you can derive the intensity of the currents by finding the Coriolis term, which can balance the pressure gradient. So in practice, whenever you see an altimetry image, then you can identify the currents as the arrows which are along the isolines of this map. Did you see already some altimetry images or not? Has anybody seen an altimetry image like this one before, or this is the first time?
No, this is the first time for me.
First time, I think I see something like that.
Okay. And then you see inside here the mesoscale eddies, so the vortices of about 100 kilometer sides. In terms of climate change, sea surface height can also be used for another obvious reason, that is to monitor sea level rise. This is a picture that represents sea level rise since the beginning of the altimetry era. So about the 90s. And you see an increase of 3.4 millimeter per year on the average with an acceleration. You can see that the curve is not really straight. The advantage of altimetry, however, is that you can map the sea surface height and even the trends all over the world, so that you can see currents, eddies, but also the spatial patterns of sea level rise. And then you see that these patterns are not trivial, but they are heavily affected by the patterns of the current themselves, since, as I said, a change in a current intensity can also modify the sea surface height of the order of a few centimeters. So a few millimeters per year, you can well imagine that can be balanced by a change in the circulation of a few centimeters per second in some region. If you look at the Western Pacific, you can see that there's an acceleration of sea level rise up to 12 millimeter per year, which is impressive. And then you can see that this is balanced in the Eastern Pacific by even a negative trend. So these are the patterns that are the patterns in the currents this time, which are affected by mode of climate variabilities, and which on the average can also modulate the patterns on the sea level rise. So how you interpret this picture? In the two bottom panels show the Eastern Pacific, showing the difference between the sea surface height observed in November 97 on the left and 2015 on the right, in respect to the average situation. So you see the presence of small spots, which now you can recognize as the ubiquitous presence of mesoscale eddies. And then you can see also some large patterns like these two equatorial bands of opposite signature that are amplified during a positive El Nino situation. Since we expect from model predictions and also from historical data a larger frequency of positive El Nino phase, this is the pattern that we expect to see stronger in the future. As you actually see, if you compare the situation of the strong El Nino in 1997 and the one in 2015. So the picture from the left with the picture from the right. If you are interested, or one day you have a project working with surface currents, or in general with environmental data for the ocean, I strongly suggest you to go to this Copernicus Marine Environment Monitoring Service. You find it on internet. It is very well done. You can make some pictures online without even you don't need even a login to, for instance, plot the presence of the mesoscale eddies from today in the region of your choice. Can be very useful if you have to work on a project related on a oceanic region. Then we go to a bit more in details. Since we are approaching the second part, we'll speak more about trophic chain in the context of marine protected areas and this trend of creating large marine protected areas in the open ocean. So this is something that you probably know. It's just a starting point. Phytoplankton needs light, nutrients, and some environmental parameters that form their niches. And then they have predation and viruses as limiting other limiting mortality factors. Sorry. We can see the distribution of phytoplankton also from satellite. In this case, we use ocean color. So basically, we send a satellite in orbit with something similar to your digital camera, and then we analyze the signal that we receive at different wavelengths. Usually there are 5 wavelengths to distinguish the signal that is typical of pigments like chlorophyll. In this case, I strongly recommend this site of Sentinel-3 satellites, from which you can easily create some impressive images of phytoplanktonic blooms, which also represent the fine-scale circulation of the ocean. The images that you find on the site, you can really explore all the world and every day for the last 5 years with an interactive map. And you can zoom inside, I think, until I think it's 500-meter resolution. It's very spectacular. And you can see the difference from the true color if you were there looking downward and the image that we can reconstruct. So at the large scale, this is a very rough image of the world. I think you have some elements of the general large-scale circulation for the ocean. So you can have boundary currents, the arrows in pink, which are separated by the subtropical gyres, which are recirculation, large-scale recirculation regions associated to relatively small currents. And then of special interest for phytoplankton, you can have upwelling regions in which, due to the presence of winds that blows along the coast, you have a divergent situation at the ocean upper layer, which is associated with the upwelling of deep water rich in nutrient. These nutrients can stimulate strong blooms and support the largest fisheries in the world. This is the contrast when you take an average of the entire ocean for chlorophyll concentration. And if you look on a specific day to a region like the one that I've put in the box in the Eastern Atlantic, then you can see that on specific days, compared to the picture which is averaged on several years, you have contrast in chlorophyll concentrations which are of the same order. So in fact, you see that the subtropical gyre is associated to values at the surface of chlorophyll of 0.1 milligram per cubic meter, 1 order of magnitude smaller than what you find at higher latitudes. But if you go to an intermediate region, you find actually the same contrast on much smaller distances on specific days. So on the top, an average over several years, and a snapshot in the bottom panel. Now, if you think of being a marine animal, what you see actually in your trips is not the average situation, is a series of snapshots. And so what you face every day are situations with strong contrast. Then you can see the importance in terms of biodiversity, because you can have very different trophic chains separated by a few kilometers and mixed together at the frontiers. And you can imagine also the importance of these structures over strategies of pelagic predators, which have to react to the presence of an Aedes and manage their currents to locate regions where their prey can concentrate. Okay, so we stop again for a few minutes here, just to see if you have questions and to exchange some comments, and then I will show some examples of the Southern Ocean. So any comment or question? Did you see something that you saw already, for instance, in other courses, or can you make some links with something that they've been presented before? Did you use satellite data already, or have you seen satellite data in other courses? Or is this the first time?
No, it was the first time for me, like to see this.
Okay. About your general background, so in terms of oceanography, for instance, when I speak about mesoscale eddy, is this something that you heard already before, a mesoscale eddy, or is something that you saw here for the first time?
I knew about like cyclonic and anticyclonic circulation, but I didn't know like what's the name about mesoscale eddies. But it's quite the same, like it's like a synonym. Mesoscale eddies is for cyclonic and anticyclonic circulation.
No, actually, it's not really. For instance, if you consider the subtropical gyre, also in that case, or a basin, a large basin, also in that case, you can speak of a large-scale cyclonic or anticyclonic circulation. In the case of mesoscale eddies, you refer to vortices of with diameters of the order of 100 kilometers. So this is the equivalent of cyclones and anticyclones in the atmospheric meteorology. So systems which have a lot of energy and which redistribute in the atmosphere the air masses on a synoptic scale, and in the ocean the water masses. So it's really, sometimes it's referred as the hydrometeorology, because it is very similar in terms of physical features to the atmospheric meteorology. And to me, it's very fascinating to think that for us, and in general for a terrestrial animal, you live on the Earth, which does not move, and then you have the atmosphere above you, which moves a lot. So during a day, you can have the weather that changes several times. In the ocean, you have these two words that makes the words in which you live. Because, for instance, a marine predator during his trip, the animal finds a mesoscale eddy, but then the eddy is also changing while the animal is exploring it. So much like an animal which is exploring a valley, and then the valley disappears. This on a geological time is impossible, because the two time scales are totally separated. While in the ocean, you have that the physical time scale of the landscape overlaps with the ecological time scale. So it's something very specific to life in the ocean.
Okay.
Okay. So about your background in terms of ocean, you know something about the general large-scale circulation, I guess. About phytoplankton, carbon cycle.
Yes, I
Did
did
you
a bit
see
like of
something?
circulation during the master, like basic circulation of the ocean between Atlantic, like the North Atlantic, South Atlantic, and same for the Pacific. And after yes, carbon cycle, a bit of chemistry, and
Okay. Is the same for all the others?
Yes, I just know the basics from masters, like how ocean circulation works, and there are eddies in the atmosphere and the ocean as well. Basics only I know.
Okay. So you are very welcome to, if I mention a term that you don't know, or there's something that is not very clear, do not hesitate to ask. So we can move to the second part. Let me share the screen again. Can you see it?
yes, it's okay.
Okay. Yeah. So we move to the Southern Ocean. Southern Ocean, I take this example to show you how in practice all the elements which I presented can go together. So to see how a large-scale circulation acts over trophic chains in an ocean basin, how the mesoscale part of this circulation can structure trophic interaction, and how this can be taken into account by a conservation plan. So very ambitious to do this in 20 minutes, but we'll try. So the Southern Ocean. Let's start with this picture with nice color. So you see in black the continents. This is easy. Then you see some lines, and these are climatological fronts. So these are lines which are not there every day, but on the average, you know that when you cross one of these lines, then on the average, you change the water mass. So for instance, you find at some point, like if you are between the black and the yellow line, you see that it is very probable that if you look at the water column, at some point you find a very cold tongue of water, and so on. And then you see a background color, which again is an average, is the average of chlorophyll concentration. So you take a lot of satellite images from surface chlorophyll concentration, then you average them, and you get these patterns. You see that you go from violet to red. Violet corresponds to the equivalent of a desert. So it means that in the violet part, basically, there's very little phytoplankton all the time. And then you see that there's a kind of band along in between, I would say, the white and the yellow line, where it's from time to time you have some hot spots of production. So you can imagine that from the point of view of marine ecosystems, this contrast have a very important effect on the type of organisms that you can find in these different regions. One advantage of the Southern Ocean is that human activity is relatively small, and also the presence of these patterns is something that we know quite well. I go back to the analogy of a terrestrial ecosystem with a marine ecosystem using this picture. So in some sense, you can see this image as the desertic part you can take as the violet part, so the ocean where there was very little primary production. And then you see this lake with this river that comes from it. Then you can see the lake as islands, which provide nutrient to the open ocean. And the slope over which the river flows is given by the currents. So we can make a zoom over the French territories. We can see again Kerguelen Islands, and then there are Croze Archipelago more to the west. And then you can see the spectacular blooms that can follow eastward from the island, and which are stretched by the Antarctic circumpolar current, which is the big arrow that I've plotted over the figure. So it's a kind of a river, if you want, with very small nutrient and with some point sources of nutrients given by the islands. You can see the presence of mesoscale features. So 1 degree is 100 kilometers. You can see in the middle, for instance, the presence of a mesoscale eddy, which is clearly corresponds to a large patch of high chlorophyll concentration. There's a rich trophic chain which develops over these blooms. So let's first look at these images from diatoms. The picture more to the right, and then going clockwise, we can go up to some top predators. The other figure is again the Southern Ocean with a model analysis with describes these plumes of nutrient which stems from the island. You can see that in the Pacific part there are no islands, and so there's no nutrient which spreads over for very long distances. So what happens in the ocean desert and what happens in presence of ocean sources? These are the two trophic chains that you can find there. If there is very little nutrient, you still have some small phytoplankton, and then you have gelatinous organisms that are very effective in harvesting them. If you have nutrients, and especially iron, then diatoms can thrive in this organism, and then crustaceans, small fish, and the large marine predators. Again, this is a sketch in which you can imagine the Antarctic circumpolar current, which goes from west to east, moving like a conveyor belt, the water that is rich in nutrient at the beginning, then in phytoplankton, then in zooplankton, then in fish, and then here you have the marine predators that are coming. They do not eat the nutrients themselves, so they are not heading necessarily close to the islands or to the seamounts, but they look for this water mass that have been enriched in the previous months of nutrients, and so where the biomass has mounted to upper levels. So this is the large-scale circulation. You see the Antarctic circumpolar current that splits in several branches around the Kerguelen plateau. And then the green dots delimit the extension of the productive region, which is stretched to the east by the Antarctic circumpolar current. So now we go to the link with conservation. This is a study that we did some time ago. The objective was to study the effect of the nutrient from Kerguelen on the production, and we saw some features, but we saw a strange minimum close to the coast. So we saw that there's a large abundance of phytoplankton close to the island. At about 500 kilometers from the island, again, we have a large abundance of phytoplankton, but then there is this strange spot in the middle, which is a minimum. So we made a model using altimetric currents, the one that I showed you before from satellite. And here you have to interpret the color as the time by which a parcel has left the island. So a red parcel has a parcel that has traveled since a long time, and a blue or yellow parcel, a parcel that is young, that has just left the island and the plateau along the island. So the interesting part is that, again, you can see this this part where the chlorophyll was lower as an old patch of water. So this is like as the trajectories that are driven by the Antarctic circumpolar currents are trapped close to the island and are obliged to recirculate. So you can imagine that you have some water parcels that are taken away. You have phytoplankton, zooplankton, and then fish when you are far from the islands, but you have this recirculation feature that can trap some water close to the islands, and then it's really like if it was a water parcel far away but trapped close to the island. Now, if you are a marine predator, you are not interested in phytoplankton, you are interested in fish, for instance. And so you are not interested in young water, which has just supported the bloom. You want some water that has supported the bloom, then zooplankton, and finally fish. So you will try to locate this region far away, where phytoplankton is probably now not very abundant because it's been eaten by zooplankton, and then you can find fish. But you can also, in principle, go to this recirculation region because here you have all the ingredients. The water has been aged, if you want, for you by the circulation, by trapping some parcels close to your colony. So if you are lazy, in the sense that you don't want to spend too much energy, you can head to this region instead of going far. So we looked at this. We took biologging data, so trajectories of marine predators that are tagged around Kerguelen. And then you see indeed that in this region there are many different species that are all concentrated. So this hypothesis of an aging water patches, which is favorable for foraging for megafauna, is confirmed. And so, putting all this together, we have been lucky enough to having done this study in the years just before France decided to extend the marine reserve around Kerguelen to the entire economic exclusive zones. So the natural reserve, which manage these waters, came to the scientific community to find some information about the regions that were more or less important to protect. And then together with the ecologist, we remarked the importance of this area of recirculation, which today is has a reinforced status. So there's no activity that can be performed on it. So this was to show how a scientific analysis can put together the circulation with primary production up to top predators, and how this information can be part of a managing plan. Today, well, in this period, we are working on a similar study for the a marine protected area around the islands of St. Paul and Amsterdam. So you see that there's a very strong will in France for creating large marine protected areas in this part of the world. The advantage is that the negotiation with other stakeholders like fisheries is relatively easy. There's some fishing, but concentrated very close to the island and already managed. The fact of protecting the large part of the economic exclusive zone can for sure accelerate the process of reaching this 30% of surface of water under marine protected areas. And this can put France as one of the countries which can act more against climate change in terms of marine protected areas. So I think I will finish here. We have some minutes for discussion, for questions. It's very special to teach at distance because I don't have any feedback from your eyes of what I'm saying. Usually, I try to understand whether what I'm saying is something that you understand or you are more or less interested. In this case, I have the impression that I speak alone. So any comment can be nice.
Thanks a lot for this presentation. It was really nice and really interesting. I just have a question about like what you presented, what you did like the past few years, I suppose. So what are you doing now? You're still studying the Southern Ocean, or you're moving to another ocean, maybe to study other bloom and other phytoplankton?
In terms of conservation, we are focusing on the Southern Ocean and on the region around St. Paul and Amsterdam. There, the mechanisms are very different because there is no more the Antarctic circumpolar current as the main physical feature that can structure the ecosystems there. Other dynamics seem much more relevant, like for instance the generation of internal waves. So the fact that because of tides, the interior of the ocean has some waves, and when these internal waves break, they create some vertical mixing. So the nutrient in this region seems not to be not to come from the islands and dispersed horizontally by the currents, but more coming from below, from the interior of the ocean to the surface, where the slower currents can move it around. So this is, and then I'm obliged to mention also a project about oil dispersion, since Gina is there under the Mediterranean, because in the framework of Gina's thesis, we are looking also at the effect of the horizontal currents in dispersing oil patches, like in oil accidents. And we are preparing to making a biogeographical study in the Eastern Mediterranean. So what was that you looked at in the other courses, in the other parts of this course actually? Hey, someone else, please. I appreciate very much that you speak, but okay.
I will tell it. So like we had a course about ocean acidification with Diana Ruiz-Pino. Was to lecture about like how emission can modify in the ocean and for many different ecosystems, and for example coral reef, and the impact. The first one I think was about more economical and strategy for the future, was general like knowledge about it. After it was about extreme climate, if I remember well, with extreme climate. After we did like geochemical impact, I think, with Matthias Beckmann, was more chemical stuff like. And I don't remember the lecture with Hervé Le Treut. I don't remember how was it. If someone was more general, I think, like about territories, about impact on territories, like more locally, the impact of climate change will impact like in different zones of the globe.
Okay. So, but here, in terms of climate change, the message that I try to pass you is that there's a tool, which is the creation of marine protected area, which can be, in some cases, very effective and possibly cheaper than other techniques. I try to put the emphasis on the fact that you cannot just take a part of the ocean and draw some lines as you wish, but you have to take into account the dynamic interaction of the water masses with life on it, with the example that we tried to did around Kerguelen. Then something that I did not say, but which is important, is that for some ecosystems, you can do whatever you want in terms of conservation, but that won't be enough. Like some coral reefs, which are vulnerable to acidification or to marine heat waves, can be protected in order to reduce additional pressure due to human activity. But anyway, if there are too many heat waves and too much acidification, they are doomed. They won't survive, and it will take hundreds of years to recover. If one day we will be back from in a pre-industrial conditions. So it's not with climate change. You probably understood that there's no silver bullet. There's no a technique that can solve all the problems. You have in terms of society, we have many options, and the marine protected area is one. It will be very important to deploy them as fast as possible and in the most effective way. So having a good scientific knowledge at the basis is very important for guiding an effective politics. Ok. Ah, sure. Oui, Josiane, tu peux arrêter. Okay, I answered to Josiane. I don't know. So the plan was to have a course until